4 دروع.
1 2 3
هاي شو بتكيل هيدا؟
شو بتكيل يا أخي؟
عند صاحبك اللي حاني بهم بتكيل هيك؟
هاي بتكيل هيك
1
شو هالكلام؟
2
شو هذا؟
3
شو 3 شو هذا؟
4
شو
هيك بتكيلوا.
لا يا
هيك بتكيلوا.
بالا مخربة بالا مخربة عشان مخربة شوفي هاوي بالا مخربة نزال سكين ما تروح لحمتك ما بيسوى.
And so, as I have said before...
No. The water clock is at last empty.
Enough. Your time is up. The water has all run out. Mud. There's mud in the water clock.
No, you must not. The clock is often clogged with dirt. Why must you clean it now? Why must my speech be made shorter?
Order! Order!
Barter and exchange, forerunner of modern systems of coinage, was a simple, even enviable method of transacting business. But scales that swing in favor of one man must necessarily cheat the other. Primitive means of measuring time, weight, and distance were a part of the primitive life a few hundred years ago. The senses of justice, of fairness, of honesty, of need for accuracy were dulled by man's lack of proper measuring tools. As life's pace through the centuries grew more rapid and its complexities increased, man, of necessity, grew more cautious, became interested in more accurate means of measuring time, weight, and distance. He began to give more attention to the problem of measurement as it concerned his personal life and the value of his property, and then considered it in relation to his neighbor's welfare. And as horizons expanded and man explored new lands, his methods of measuring distance necessarily became finer. As he became more observant, time assumed more value in his personal and public life, and so his sense of time became sharper. Weights, as diversified as the people who originated them, and most commonly subject to inaccuracy and fraud, also came under man's surveillance. They gradually approached a standard. More delicate, more sensitive instruments were developed to aid him in determining the extent of his possessions and purchases and in plotting his course. During these centuries, measurement of time dwindled from days to hours, to minutes, to seconds. Finally, seconds were divided into hundreds, thousands of parts. Fine measurement did not stop at the weight of a seed, but went on to the weight of a grain of sand, the weight of an eyelash. Haphazard measurement of length gave place to the standard yard, the standard inch, and the single inch was divided into 10,000 parts.
Today, accuracy and precision have taken on new meanings. Split seconds, hundredths of an ounce, thousandths of an inch have become of vital importance in the exploration of new worlds of science, invention, and development. New instruments, new and delicate measuring devices have added to the power of man's senses. Now science knows the answers to such questions as, how long does an explosion last? That question is answered in laboratories where the 24-hour day has been divided into millions of split seconds. How fast is an electric spark? Not so fast that it cannot be measured to the thousandth part of a second by the electric oscillograph. How flexible is steel? The amount of bending of a railroad track under tons of speeding weight is easily visible. But science has gone far beyond ordinary rules of measurement. We can measure the movement of the same steel rail under the light pressure of a finger. With the delicate electric telemeter, the movement in the section of the railroad track can be measured in millionths of an inch, 8 millionths under the pressure of a few ounces. How small is 8 millionths of an inch? Compared with the average thickness of a human hair, magnified thousands and thousands of times under the microscope, 8 millionths of an inch would correspond to the thin white line in the center of the hair. That's how far the finger bends the rail. How heavy is a speck of dust? How much does smoke weigh? How much does a tiny black dot from a lead pencil weigh? The finest scales can tell, scales operating on so fine a balance that they must be enclosed in glass and the air artificially conditioned. Scales so sensitive that the breeze from a moving hand would completely unbalance the indicator. And the answer comes not in ounces, but in millionths of an ounce. A slow, tedious job, weighing minute particles. But the patience of science parallels the precision of its instruments, reaching into the world of the infinitely small, interpreting it in terms of the new language of measurement. The tiny dot from the lead pencil can be magnified until we see the fibers in the sheet of paper. And the scattered bits of black are as big as chunks of coal. With microscope lenses that carry us farther and farther beyond the range of the human eye, we can lose ourselves in a newspaper reproduction of a photograph until nothing is left but meaningless dots. How sharp is a sharp edge? The cutting blade of a pair of scissors, under the searching eye of the microscope, appears rough and jagged. The peaks and valleys on the edge of the blade can be easily seen. What's in a mixture? How many parts of this and how many parts of that? A beaker full of water from a large swimming pool, and mixed with all the water in that pool, a single teaspoonful of salt. How much salt is in the beaker? Finding the answer is as complicated as finding one man in a crowd of hundreds of thousands of people. But the presence of infinitely small particles of matter can be detected when the residue from the beaker is burned and a picture of the flame taken with a spectrograph. The teaspoonful of salt in the swimming pool leaves its signature of tiny lines on a photographic film.